In this video, we talk about a combinational circuit. The first question we want to ask, what is a combinational circuit? In the previous video, we have designed a circuit that implement Boolean function, for example, f(x,y,z) equal to x or y not z. So in fact, this is an example of a combinational logic circuit because that the function implemented by using the OR a logic circuit and not logic circuit, and also the AND logic circuit right here. So that's the combination of multiple logic circuit together. One of the key, very important of the combinational logic circuit that the circuit produce a specified output almost at the instant when the input value are applied. Later on, we can see that there are many other logic circuit that doesn't have this property. That's got a service called a consequential circuit. Okay. One of the very important combinational logic circuit that the half-adder circuit. So basically, the half-adder circuit that perform the summation of the two input bits. And let's see how the half-adder perform by looking at the truth table on the right hand side right here. So we have the two inputs x and y, and the output gonna be the sum and the carry out. Okay. When the inputs x and y equals 0 and the sum equals 0 and the carry out equals 0. So basically just the add of two bits 0. Okay. 0 add 0 equals to 0 and nothing carry out. Now if x equals 0, y equals to 1, or x equals to 1, y equals 0, we have the 1 plus 0, that equals to 1. Okay, and there's no output bit, carry out bit. Okay, the same when the x equals 1, y equals 0. Now, in the case x equals to 1, y equals to 1, we have the 1 plus 1 equal to 1, 0. Okay, so the sum color equal to 0 and the carry out bit equal to 1. Okay, so that's basically the half-adder circuit. So the next step we see how can we achieve the half-adder circuit by using some of the basic logic gates. So you can see that actually the half-adder can easily constructed by using a XOR gate and a AND gate. Okay, so basically the inputs x and y gonna be fed into a XOR gate to get the sum and fed into the AND gate to get the carry. So let's see if that's correct with the truth table based on the circuit we constructed right here. Okay, so let's say x equals 0, y equals 0. We have the 0, 0 into the XOR gate, so the output going to equal 0 because the input are the same. On the other hand, if you have the 0, 0 to the AND gate, the output also equals 0. So we have the sum equals 0, carry equals to 0 when x equals 0 and y equals 0. So that's the first row correct. Now, if x equals 0, y equals to 1, so the 0, 1 to the XOR gate, the output is equal to 1. Okay, and because the inputs values are different. Okay, on the other hand, if we have the 0 and 1 to the AND gate, the output equal to 0. So the sum equal to 1, the carry equal to 0. So that's the second row in the truth table right here. The next one, when x equal to 1, y equal to 0, this is similar to the previous case. We have the 1, 0 to the XOR, the output equal to 1, and 1, 0 equal get into the AND gate, the output equals 0. So that's the third row in this truth table. The last case when x equal to 1, y equal to 1, so 1, 1 get into a XOR gate, the output equal to 0, right? Because of two of the bits are the same, the output equals 0. Now, 1, 1 get into the AND gate, the output equals to 1. So we have the sum equals to 0 and the carry out equals to 1. Okay, so basically the circuit combination of the XOR and the AND gate with this structure form a half-adder circuit. Okay. Now the next one we study about the full adder circuit. So basically the full adder circuit gonna have allow us to not only perform the addition of two input bit x and y, but also have some carry in bits as well. Okay. So let's see what is the full adder gonna perform. So basically the full adder have the input x and y, and the carry in is the can also be a 1 or 0. So if x equals 0, y equals 0, and carry in equals 0, the summation of all the information of x, y, and carry in is gonna equal 0, and carry out also equals 0. If x equals 0, y equals to 0, carry in equal to 1, so we have the sum equal to 1, right? We add them all together, so this is equal to 1 and carry out equal to 1. The similar situation when x equals 0, y equals to 1, and carry in equals 0. Okay. Now let's see if x equals 0, y equals to 1, and carry in equal to 1. So we add them all together. 1 plus 1 equals to 1, 0. So the sum gonna equal to 0, and the carry out equal to 1. Okay. So the other scenario gonna be the same. Now the last scenario right here, we have the x equal to 1, y equal to 1, and carry in equal to 1. So we have the 1 plus 1 plus 1. So the result gonna be a 1, 1, right? So 1, 1 gonna have the sum equal to 1, and the carry out bit equal to 1 as well. Okay. So that's the truth table of the full adder circuit. The next question we want to ask is that is there any way we construct the full adder based on the half adder we discussed before? So basically, we the half adder we have the is constructed by using the XOR gate and the NAND gate as we saw right here. The answer is yes. Actually, we can construct the full adder by using the half adder in the following way. The first adder gonna be used to take the inputs x and y, and the output of the first half adder gonna be combined with the carrying bit and to fit into the sum of the second half adder. Okay, so this is the first half adder right here. This is the second half adder right here, and the carry out the two half adder combined through the OR gate to create the carry out bit of the full adder. Okay, so let's see is that the constructed circuit produce the truth table of the full adder we discussed before. Okay, so let's say if x equals 0, y equals 0, and carry in equals 0. So we have the 0, 0. The output of the XOR operation, XOR gate right here equal to 0, and 0, 0, and the output equals 0. Okay, so the sum of the full adder equals 0. Now, if x equals 0, y equals 0, so the inputs of the AND gate right here equals 0, 0, so the output equals 0. Okay. On the other side, we have the output here equals 0. We go into another AND gate right here with the carry in equals 0. So we have the two inputs 0. The output of the second AND gate also 0. So we have the 0, 0 fed into the OR gate. So the output of the OR gate equals 0. So the carry out of the full adder equals 0. Okay. So the first row have been verified. Let's say now we have the x equals 0, y equals 0, and carry in equal to 1. Okay, so 0, 0, and 1. So the same as before, we have the output of the XOR gate right here equals 0, and this one equal to 0. Now we have the carry in equal to 1. So 1, 0 fed into a XOR gate, the output gonna be equal to 1. So that's the sum. Now we have the 1 right here, we have 0 right here, the output equal to 0. Another output of the another AND gate equals 0. So we have the 0, 0, and the output of the OR gate with two inputs 0 equals 0. So the second row have been verified. Okay, so let's consider the row where x equals 0, y equals to 1, and carry in equal to 1. Okay, so we have the 0, 1, and 1. So if 0, 1, the output equals to 1, right? Because the inputs are different, the output of XOR gate equal to 1. So we have the 1, 1 right here, fed into another XOR gate right here. So the output equals to 0, right? Because the two input are the same, the output of the XOR gate equal to 0. Now we have the 1 right here, so the output of this AND gate equal to 1. We have the 0 1, so the output equals to 0. So 0 1 and fed into the OR gate, the output equal to 1. So the sum equal to 0 and the carry out equal to a 1. So that the this row, when x equals 0, y equals to 1, carry in equal to 1. So we have the 0 1. At the sum and the carry out of the full adder. Okay, let's take another look at the last row when x equals 1, y equals 1, and carry in equal to 1. Okay, so 1, 1, and 1. So when x equals 1, y equals to 1, the output equals 0. Because the same input for the XOR gate, the output equals 0. 0, 1, so we have the output of the XOR gate equal to 1, right? So now the sum equal to 1. That's correct right here. Now we have the 1 right here, and the output of the first XOR equals 0. So we have the 1, 0. So this output of this AND gate equals 0. Now we have the 1, 1 right here. So the output equal to 1. So 1, 0 fed into the OR gate, the output equal to 1. So we have the carry out equal to 1. So the last row also had been verified. Okay, so you can see that the this constructed full adder based on the two half adder is valid and or produce the correct answer for the full adder. Now, the next concept we discussed is the ripple carry adder. So basically, ripple carry adder is mean we before we discuss the half adder and also full adder that in a single circuit. Okay, so now the scenario of ripple carry adder is mean we put them all together in a such a way the carry out of the previous one can be fed into the next adder. In that way we can perform the addition operation of the larger string of bit 0 and 1. Okay, so this is a way we constructed it. So we have the first full adder right here. We have the two inputs x naught and y naught with the carry and c naught. Okay, so this one have the carry out. This is the C1, okay, and the carry out C1 gonna be add, so we have another output right here. That's the sum of the first full adder. Okay, the carry out C1 right here gonna be fed into the second full adder with the inputs H1 and Y1, and keep doing like that. We have the output of the second full adder gonna fed into the third full adder and so on. Okay.